Okay, we're in Chapter 2, Section 4 of Barnett, and we're looking at polynomial and rational functions. Several objectives for this section. The first one will be to graph and identify properties of polynomial functions. So that's what we'll work on first. We'll start with the definition of a polynomial function. A polynomial function is simply a function that can be written in this form that you see here. A sub n x to the power of n plus a sub n minus 1 x to the power of n minus 1, etc., all the way down to a sub 1x plus a sub naught. N has to be a non-negative integer, and it's called the degree of the polynomial. This is sort of the highest power that you'll have here. The domain of a polynomial function is always the set of all real numbers, because any input here is allowed, and you will get an output. A polynomial of degree 0 is what we call a constant, and a polynomial of degree 1 is what we've seen before as a linear function, right? The good old y equals mx plus b. The degree here is 1. Polynomial of degree 2 was the topic of the last section. That was just a parabola, right? The graph was a parabola, rather. It was a quadratic function. So you've already worked with some of these polynomials of degrees 1 and 2. In this section, we just expand our picture. So we look at more polynomials, different degrees. Okay, well, polynomials can be further broken into odd or even. So a polynomial is called odd if it only contains odd powers of x. Okay, so for example, x to the fifth plus x cubed minus plus 7x. There you go. That's an example of an odd polynomial. And it's called even if it only contains even powers of x, like x to the fourth minus 3x squared. That's an even polynomial. Well, anyways, we're going to look at more of these. And let's look at the shapes of some of these even and odd polynomials. And let's look for some of the following properties. So as we see the graphs that follow here, look for symmetry. Look for the number of x-axis intercepts. In other words, the number of x-intercepts. The number of local maxima and minima. And what happens as x goes to positive or negative infinity. So let's take a look. Here is the graph of f of x equals x minus 2. So that should be an odd power, right? Because we only have the power 1 here. And a constant. And let's see. We go from being negative to being positive. That's one observation. Same here with x cubed minus 2x. Once again, we go from being negative to being positive. For both of these examples, there seems to be a symmetry with respect to the line y equals negative x. If I sort of draw it out dashed here, it served as a mirror image to both of these pictures, right? Here's the line y equals negative x again. So notice that symmetry. So these are odd because the powers of x are odd only, 3 and 1. In this case, 1 in the previous case. Okay, notice the power was 1, 1x intercept. The power here was 3, we had 3 x intercepts. When I say power is 3, I really mean the degree is 3. Okay, how about this one? X to the fifth minus 5x cubed plus 4x plus 1 seems to be odd again, right? Only odd powers of x. And if you were to draw the line y equals negative x, once again you will get that natural symmetry going. Notice starts out negative again, just like the previous two, and ends up positive as x goes towards positive infinity. And notice we have 1, 2, 3, 4, 5 x intercepts, and the highest power of x, or the degree of the polynomial, is 5. Okay, here's another one, x squared minus 2x plus 2. Be careful, this one's not even because there's a power of x that is odd, namely this one, right? That's a power of 1. The highest power is even 2. However, there's this is not what we call, what our book calls, an even polynomial. So you guys know that the graph is a parabola, and you know about the line of symmetry here. Okay, and notice as we go towards negative infinity, this graph is very positive, and if we go towards positive infinity, this graph is still very positive. Starts at positive infinity, ends at positive infinity. Okay. Let's take a look at another example. Again, this is not an even one. It might look like it is, but be careful. This power here is odd. And what I want you to notice is this has power 4, but notice it crosses the x-axis only twice. Okay. Once again, positive and very positive as x approaches negative infinity. Very positive as x approaches positive infinity as well. Okay. One more example here. X to the 6 minus 7x to the 4th plus 14x squared minus x minus 5. Again, this is not even because we have an odd power of x here. We have only 1, 2, 3, 4x intercepts. Yet again, positive infinity as x approaches negative infinity. Positive infinity for the values of h as x approaches positive infinity. So what we could summarize here, our observations from all these graphs, are those that for an odd polynomial, the graph is symmetric about the origin. That's what it means to say symmetric about the line y equals negative x that I was drawing in for you. It's the same thing to say those two terms. About the origin is the same as saying symmetric about the line y equals negative x. The graphs start negative, end positive, or vice versa, depending on whether the leading coefficient is positive or negative. So you saw that with all the odd polynomials. All our leading coefficients were positive. The leading coefficient is that a sub n in your polynomial. Okay, so if you had your polynomial, this is the leading coefficient. The coefficient that that is attached to the variable that has highest degree, right? The a sub n. Okay, and if that's positive, then for the odd polynomials, in that case, the graph starts positive and ends positive. Started negative, excuse me, and ended positive, is what I should say. Alright, and had it been flipped, if a sub n was negative, then the graph would start positive and then end negative. Either way, a polynomial of degree n crosses the x-axis at least once, and at most n times. Okay, at most n times. So if it was x cubed, then it crossed the x-axis at most 3 times. If it was x to the 5th, the degree was 5, it crossed at most 5 times. On the other hand, in the even polynomials, the graph is symmetric about the y-axis usually. So think of these, we didn't see many examples of these in the graphs, but think of y equals x squared, right? Which is the basic parabola. You could do y equals x to the 4th on your calculator. You get a W shape that's symmetric about the y-axis. Okay, let's see. It says the graph starts negative, ends negative, or starts and ends positive, depending on whether the leading coefficient is positive or negative. So you remember when we were graphing in the previous section quadratics, if the a here was positive, the parabola opened up, so it was positive and positive at both ends. This is if a is positive. If a is negative, then the parabola opened down. Okay. Either way, a polynomial of degree n crosses the x-axis at most n times. It may or may not cross at all, right? So you've already seen an example of this. If we have x squared plus 2, the graph of it looks like this, where this is 2, does not cross the x-axis at all, right? So it crosses at most n times yet again, but it doesn't have to cross at all. Okay, so some characteristics here of polynomials that your book mentions, and you should read about in more detail. Graphs are always continuous for polynomials because any input is possible. We'll talk about that more later. One can sketch the graph without lifting up the pencil. That's the definition of continuous we're sticking with for now. And like I said, we'll expand on this later when we learn about limits. Graphs of polynomials have no sharp corners. These are also called cusps. Graphs of polynomials usually have turning points, which is a point that separates an increasing portion of the graph from a decreasing portion. And let's see, a polynomial of degree n can have at most n linear factors. Therefore, the graph of a polynomial function of positive degree n can intersect the x-axis at most n times. So, once again, a polynomial of degree n may intersect the x-axis fewer than n times, right? And that's something that we saw.